Welcome back to the Physics Chalkboard. Today, we're tackling one of the most exciting topics in kinematics, projectile motion. We've been building up this lesson step by step. So far, we've reviewed vectors, kinematics of straight-line motion in the horizontal direction, and vertical motion, also known as free fall. Today, we're putting these together into two-dimensional motion. If you've ever wondered how to calculate a projectile's speed, range, flight time, or maximum height, you're in the right place. Let's dive in. Projectile motion occurs when an object moves in both the x and y directions at the same time. This happens when an object is projected and is under the influence of gravity only, no other forces acting on it. In our model for projectile motion, the only force acting on the object is its weight, the force of gravity. This means there are no horizontal forces. According to the law of inertia, if no force acts in the horizontal direction, the horizontal velocity remains constant throughout the motion. Meanwhile, the vertical motion is simply free fall under gravity. We can describe both the horizontal and vertical motions mathematically using the kinematic equations. For the vertical part, just apply the same formulas you learned for free fall. If you need a refresher, check out our previous video on free fall. For horizontal motion, the acceleration is zero because the velocity remains constant. This means some kinematic equations don't apply here since they involve acceleration. With a equals 0, terms that include acceleration drop out, leaving us with a much simpler equation for horizontal displacement. Look, this is 0, so that one is 0. This one is 0, so this one too is also 0. Well, here, this term is 0. We are left with this then. If we make that horizontal, it becomes distance in the x equals velocity in the x multiplied by time. So that's the mathematical description. But how does it look in real motion? With uniform horizontal velocity and constant downward acceleration, the object moves forward while gravity pulls it down. The result? A curved path that bends downward, forming a parabolic trajectory. Let's explore these scenarios through this example illustration. The object has to be projected at an angle, like this one. Its velocity is that orange vector that is angled up. While in this scenario, velocity vector is that orange arrow that is angled downward. Lastly, in the third illustration, it can also be this one, completely horizontal in the beginning. Let's zoom in on these diagrams of initial velocities. Whenever a velocity is shown as a single angled vector, we can break it down into two simpler parts, its horizontal component and vertical component. These components make it much easier to analyze the motion mathematically. The first one has a positive vertical component of velocity, shown here as a green arrow pointing upward. The horizontal component is also positive because the object is launched toward the right. The second scenario has a negative vertical component of velocity, so the green arrow here is pointing downward, while the horizontal component is positive. While the third has zero velocity in the vertical. This means that the initial velocity is completely horizontal. Mathematically, this tells you that the initial velocity here is already v sub x. When you start solving problems on your own, pay close attention to how the initial velocity is stated. In some cases, the problem will already provide the velocity in terms of its horizontal and vertical components, so you won't need to calculate them yourself. Let's try an example. The problem says, a football is kicked at an angle above the horizontal, giving it a vertical velocity component of 20 meters per second and a horizontal velocity component of 25 meters per second. We need to solve for the initial speed, the time of flight, the horizontal distance traveled, or range, the maximum height. And that seems like a lot to find, and we only see two numbers, 20 and 25. But those two values might be all we need. Notice that 20 meters per second is the initial velocity in the vertical direction, v sub y, and 25 meters per second is the initial velocity in the horizontal direction, v sub x. The first thing you should do is illustrate the vectors. Simply listing the given values may not be enough, especially if you're just starting out. A good diagram helps you visualize the motion and organize the information you need to solve the problem. So let's draw an exaggerated illustration, focusing on the vectors only. The angle is above the horizontal, meaning to say it should look like this one. Here is a vertical component, shown as a green arrow pointing upward 20 meters per second. While this one is the horizontal component, the blue arrow, 25 meters per second. If we trace the trajectory, it will look like this. So, what do we know from the diagram? First, take a look at this orange arrow. It represents the initial velocity of the football. If we can find the magnitude of this vector, we've already answered the first question. The initial velocity is made up of two components, 20 meters per second vertically and 25 meters per second horizontally. These form the two sides of a right triangle, with the unknown hypotenuse representing the actual initial speed. To find it, we can simply apply the Pythagorean theorem. Let's calculate it. Using Pythagorean theorem, we find that the initial speed is 32.02 meters per second. What's next? We need to determine the time of flight, the total time the football stays in the air, from launch point to landing point. What do we know about these points? By using the symmetry of vertical motion in freefall, we know that the vertical velocity at the landing point is the negative of the initial vertical velocity. So if the ball starts at positive 20 meters per second, it will have negative 20 meters per second when it comes back to the same level. The time of flight is the time to change the vertical velocity from 20 meters per second to negative 20 meters per second. Try to make sense of that before you look for a formula to use. See that the velocity is changing as it moves from here to there. How is it changing? It is changing by negative 9.8 meters per second, meaning to say, after a second, this velocity is now just 10.2 meters per second. Then it becomes just 0.4 meters per second. Then, on the next second, it is now negative 9.4 meters per second. Then finally, on the fourth second, it is negative 19.2 meters per second. That is already very close to the final velocity here at the end point, so we can guess that we are looking at 4-something seconds as the answer. Let's do that accurately by doing our math. Okay, given initial vertical velocity 20 meters per second, final vertical velocity negative 20 meters per second, acceleration due to gravity negative 9.8 meters per second, find the time of flight. Now, pull out your list of kinematic equations and focus on the ones for vertical motion, because all the quantities we're working with, velocity, acceleration, and time, are in the vertical direction. Take a moment to choose the right equation. Got it? Great! You should have picked this one too. Let's solve it quickly. After substituting the values and simplifying, we find that the time of flight is 4.08 seconds. That's very close to our earlier estimate, which gives us confidence that our approach is correct. A quick reminder, when working through the equations, be consistent with your signs. If you ever end up with a negative value for time, something is wrong in your setup. Go back and check your steps. The next question is a quantity in the horizontal. The total distance covered in the horizontal is called the range of the projectile. Looking back at the illustration, the horizontal velocity is 25 meters per second, and it stays constant throughout the flight. This means the object moves 25 meters every second, as long as it's in the air. In other words, after 1 second, the ball has traveled 25 meters. After 2 seconds, 50 meters, and so on. If we know how long it stays in the air, we can easily calculate the range. And we do know that. The time of flight is 4.08 seconds. So let's organize our solution. Given the initial velocity in the horizontal of 25 meters per second, which is a constant, so this is also the average velocity, and time of 4.08 seconds, find the distance. Let's call that x. Let's do this quickly. From your list of formulas, this distance is x equals v of x multiplied by time. Okay, so the range is 102 meters. List down your questions if you need anything here clarified when we discuss it live in class. Next, let's find the maximum height. This is a vertical quantity, so let's go back to the diagram and inspect what we have, which could tell us about it. That maximum height is here. What do we know about this point? The vertical velocity here is 0. Using symmetry of time, until this point here is half of the flight time. We have plenty to work with, so let's list them down. Given the initial vertical velocity of 20 meters per second, final vertical velocity of 0, acceleration due to gravity of negative 9.8 meters per second, and time of 2.04 seconds, find the y maximum. Okay, 5 seconds. Try to figure out which equation can you use. Did you pick this one? Great. This equation gives us the maximum height of 20.41 meters. There are actually several ways to solve for the maximum height in this problem, since you already have plenty of information given. I'll leave that for you to explore. And that's it. We're done. Did it seem easy? It should, because we've been building up to this point step by step. If you've been following along, you strengthen both your understanding of kinematics and your algebra skills. But don't stop here. Practice more problems on projectile motion to master it. This one is for you to try. Take a screenshot of this problem and solve it on your own. The problem states, a long jumper leaves the ground with an initial vertical velocity of 8 meters per second and initial horizontal velocity of 9 meters per second. Find the following: time of flight, maximum height, and finally, the range. What do you think? Share your solutions or any questions you have in the comments below. I'd love to see how you approach this. And that wraps up our walkthrough on projectile motion. I hope this step-by-step breakdown helped make the process clearer and easier for you. If you found this video helpful, give it a thumbs up and share it with your classmates. Don't forget to subscribe and hit the bell icon so you don't miss the next Physics Chalkboard episode. Got questions or your own solutions? Drop them in the comments below. I'd love to see your work. Until next time, keep exploring physics.